Today we will look at the two final theorem for this chapter. Okay. From last week, we know that when a point x star is a local minimizer of the objective function f, then the gradient of the objective function at that point at x star must be zero. It must be a zero vector. If x star is not a zero vector, then we know that it cannot be a local minimizer of the function f. Okay. Then today we will move to the what we call another necessary condition. But this is stated in terms of the Hessian matrix, and therefore it's called second order. Okay. Again, here we have to make assumption. First, we assume that the function f is twice continuously differentiable. So from this assumption, you can guess that the consequence that we will use is that the Hessian matrix is continuous, right? The Hessian, as a consequence of this is the Hessian matrix is continuous, and therefore the Hessian matrix is symmetric matrix. That means we can interchange the order of the partial differentiation. Okay. Now, if the point x star is a local minimizer of the function f, what happens? Okay, we'll see. We already know from the previous theorem that if f is a local minimizer of the function f, then the gradient is a zero vector, right? From the previous theorem. But here in this theorem, we will prove that the Hessian matrix must be a positive semi-definite matrix. Right? So what you can see from we will go through the proof first. In this proof, we use contradiction method. Oh, sorry. No, sorry. Let me see. Yes, we used a contradiction method. You can see here when you see this phrase. If you have to assume by contradiction, that means this is a way to tell readers that you are going to use contradiction method. You don't have to, but just okay. But for professional mathematicians, they already know. But okay. But if you want to make it clear so that the reader can prepare themselves to read this, then you just say that, okay, assume by contradiction. Okay, now you see, so we have two statements. We have two statements. We have two statements, A and B. So the statement A is X star is a local minimizer of F. And statement B is the Hessian matrix is positive semi-definite. Okay. Now when we prove what we want to prove, by contradiction. Okay. Okay. We want to prove. We want to prove that A implies B, right? By contradiction. So what we have to start? How do we start here? So we have to assume. We have to make two assumptions. First, assume A holds. And two, assume by contradiction that not be false. So what? Okay. So here we have to assume. So first we assume in here we assume that x is a local minimizer of the function f, and then we assume by contradiction that the Hessian matrix of the function f at the point x star is not positive semi-definite. So when we assume, so what is the concept? Well, okay, from here, then we will see what happens. Okay, okay, x is a local minimizer from the previous theorem. Okay, x is a local minimizer plus that the gradient of f is 0. Okay? We will use that. And from the second step, right, which is from the second one, we assume that the Hessian matrix at x star is not positive semi-definite, not PSDF. So what does it mean when it's not? When this is when the matrix is not positive semi-definite? When a positive now, according to the definition, right? F is a positive semi-definite. Sorry, the Hessian matrix is positive semi-definite. Okay, if and only if the quadratic function x transpose multiplied with the matrix multiplied with x is greater than or equal to 0 for all x, right? So what is the negative for, okay? So we have, okay, so we write it down. The statement, the not B, okay? Not B. What is B? B is that the x transpose the Hessian matrix of x, right? Now you see x is an arbitrary vector in, it can be any vector in Rn space, right? X transpose the Hessian matrix X is greater than or equal to 0 for all X. So when this is, so the negative statement of this is what? What is negative statement of this? So the negative of this is, there exists, well, for some X, right? For some X, what happens? For some X, the X transpose, the see here, this happens for all X. Let's look at this. This happens for all X. When the negative statement of this is when F is not positive semi-definite, then that means for some X, this may true or this may not true, right? Because we have positive semi-definite and negative semi-definite and indefinite. So that means for some X, right? The Hessian matrix is indefinite. The Hessian matrix is indefinite. for some x, the h, oh no, that means, moment, is equivalent to the fact that the is indefinite matrix, is an indefinite matrix. So that means, so and this is equivalent to, for some x, right? That means there exists. Okay, here we call it a vector p. So it can be positive or it can be negative, right? When when you see when the H matrix is positive semi-definite, all the eigenvalues are real and non-negative. When the H matrix is not positive semi-definite, that means some of the eigenvalue can be positive, or some of them can be negative, or some of them can be zero, right? Okay. Then that means this is what happens when the H matrix is not positive semi-definite. It can be negative semi-definite or indefinite, right? Am I right? There are three possibilities: a positive semi-definite, negative semi-definite, and indefinite. Right? When it's not positive semi-definite, it can be either of them, either of the other two. Right? So that means okay. So this is what we arrive at. This is what we arrive at. Okay, from the assumption that the H matrix is not positive semi-definite, right? Okay, and we will use this vector p. This vector p will be used in the proof. There exists a vector p such that the p transpose the H matrix at this point p is negative. Okay, this is what we. Then from this, okay, we will consider the Taylor series expansion of the function f up to the second order, right? In this direction, in the direction of the vector p. So we consider the Taylor's expansion of the function f in the direction of this particular vector p. This is the part x. Okay. Then this is the vector p, right? This is the vector p. Then we consider the Taylor's expansion of this. Okay, so what is the Taylor's expansion of this? Then we consider the Taylor's expansion. Why we use Taylor's expansion? Now you say because x is a local minimizer, then we will use the definition of the we will consider. Okay, we will look at what the function have, what the function f, what the objective function f behaves in the vicinity or in a small region around the optimality, around a local minimizer, around the point x star. Okay. So we look at the Taylor's expansion, the Taylor series expansion of f about point x star. Okay, along the direction p. Okay. use the f of x star plus p is fx star plus the gradient, plus the gradient star transpose p, right, plus 1 over 2 x 1 over 2 p transpose. The Hessian matrix of x star plus alpha p, right? If you remember this, times p for alpha is a constant between 0 and 1. Right? And then when we, this is okay, this now, because here this is an equation. So the left-hand side is equal to the right-hand side. It's exactly equal to the right-hand side. And this is what we have the extra variable, the alpha right here. So here we consider the alpha in when we consider the what and the vicinity or the neighborhood of the function of the point x star, then the alpha must be very small, right? The alpha must be very small. So for okay, the alpha is very small. Sufficiently small in mathematics, we say for sufficiently small alpha. So that means the alpha is less than, is greater than 0 and much and less than now for sufficiently small alpha. So that means um, alpha is positive, right? But is less than alpha bar, where alpha bar is the upper bound. That is when we consider an open ball, then the alpha bar is the radius of the open ball that defines the neighborhood of the function. Okay, that the alpha bar is the radius of the neighborhood. Alpha bar is much less than 1. So means here we go back to this. We draw no. Here we use the green color. The alpha bar, okay? Consider the neighborhood around this point. Then you see that, okay, now we will, okay, now for sufficiently small alpha, we use the continuity of the function f. We will use the well, to be precise, we will use the continuity of the Hessian matrix. Don't forget. Here the assumption the assumption we make here is that the function f is twice continuously differentiable, right? So the H matrix is a continuous function of f. Sorry, if the H matrix is continuous in the x variable, right? So that means each element of the H matrix is a continuous function of the vector x, and the H matrix itself is symmetric. That's the consequence of the assumption that the function f is twice continuously differentiable. Now, you see that when okay, so that means the what? That means P transpose the H matrix of the function f. Well, plus P, right, is negative, implies that, okay, implies that P transpose the H matrix of the function f at the x plus the alpha P must also be negative, right? Because this quadratic function cannot change the sign immediately when the H matrix is a continuous function of x, right? For alpha less than alpha plus. Right? That means within this yellow ball, within this yellow sphere in the Arun space, the H matrix, the quantity P transpose the H matrix at the point x star plus alpha P, sorry, alpha P times P must be a negative number, right? Okay. If you don't see this immediately, then you may take some time. You may need to spend some time understanding this, right? And then what happens then? Now this is the key conclusion that we will use to make the contradiction. Then when from the Taylor's expansion, okay. Now we go back to the Taylor. Look at the Taylor's expansion. This term is 0, right? Because x is because x is a local minimizer. So the gradient at that point is a 0 vector. Then now you see, this is the conclusion that we have made so far. We make the conclusion that this term is negative. Then from the Taylor's expansion, fx star plus p is equal to fx star plus something which is negative. So now you tell me which one is greater, fx star plus alpha p or fx star. Right? This term is negative. This term is negative. Right? When this term is negative, then okay, I write it again. Fx star plus alpha p is equal to fx star, right, plus the graph fx star transpose p plus 1/2 alpha square p transpose the H matrix plus something. Okay. Now you check this. You can define that as a lambda or something. Okay. multiply with P for lambda is between 0 and 1, right? Okay. Now, from this, you see that this one is 0, right? By the consequence of the first order necessary condition. Now, from the above discussion, we know that this term is negative. This term is negative. The highlighted term is negative. Then fx star plus alpha p is equal to fx plus a number which is negative. So which one is greater? Fx star is greater. So that means, so this implies that fx star greater than fx star plus alpha p, which contradicts the fact that the assumption that f x star is a local minimizer. The function f, right? And that's the end of the proof, the QED. I will upload this, okay? I will upload the slide I write today to the Microsoft. Microsoft team. Okay, you can see that later. In this time to digest. I remember very well when I first when I did my master here with my professor. She's already retired many years ago, and uh, that was the first time I faced the proof by contradiction. It took me quite some time to understand this. Okay, and if you want to see this, okay, the proof, well, actually, the proof is already here, but this is taken from the book Numerical Optimization by Nosadal and Wright. I think it's in our. This book is a reference, okay, in the course syllabus. You can download this from a Sprinkle Link database through Chulalongkorn. Nosadal and Wright. Professor Nosadal is still teaching at University of Northwestern. I think, yeah, Northwestern University in Illinois. Myself, that's the title of the book. Do you have any question? Okay. Let me finish the proof first. Okay. If in case you may have that later, and you can ask me after we stop recording. Okay. Next one, we move to the next theorem, which is the second order sufficient condition. Now, here when you say sufficient condition means the condition that is sufficient to conclude that a point x star is a local minimizer of the function f. So what are they? This is what we have to prove here. Okay. So we will This condition implies that X star is a local minimizer of F. So this condition is what we call a sufficient condition, right? For optimality. Okay. We will see here what is this. Okay. Now here we, as usual, because we this is second order condition, so we have to make sure first that the Hessian matrix exists, and also it must be a continuous function, right? So here we suppose that F is twice continuously differentiable. Okay, so if the gradient of the function f at the point x star is a zero vector, and if the Hessian matrix of the function f at that point is positive definite, then we can conclude that x star is a strict, local minimizer of the function f. Again, here we will to conclude that x star is a local minimizer of the function f. So what we have to do? Now we look at this is the, okay. Hmm? Hmm. So this is the point x star. If we want to conclude that the point x star is a local minimizer, then we have to consider an open ball, an open sphere in Rn, right, which is the neighborhood of the point x star, right? So we look at the point with the small radius. This is with the epsilon bar. Epsilon bar is the radius, right? Where the epsilon bar is very small. Okay. Then for any point, okay. So this is okay, now what is this? How can we define this open sphere? We define this in the neighborhood, right? The neighborhood of the point x star with the radius epsilon bar is a set of x in Rn, right? Such that the norm of x minus x star is less than epsilon bar, right? Right? Correct? This is the neighborhood. Okay, it defines an open ball or an open sphere. Open sphere in Rn around the point x star. Okay, so what happens here? So when x is a local minimizer, you see that x star is a local minimizer of f is equivalent to the fact that fx star is less than fx, right? For all x. that is in this neighborhood, right? And x is not equal to the point x star. Right? This is by definition. We already see this definition already, right? We see this definition already at the introduction of this chapter. This is the definition, right? And okay, just remind you that this is the definition of a local minimizer of f, right? If you agree, if you agree with me for this, then I'll move on. Then what we do is that we look at the Taylor's expansion. Again, we look at the Taylor's expansion. Okay, now we consider the Taylor's expansion of f about x star, okay, for all x in this neighborhood. So for all x in this neighborhood, how can we represent this? So usually in this, you can go to any direction around the point x star, right? And then for any direction that you move away from the point x star, in as long as the point is in this open ball, then the fx star must be less than fx, right? Now we will look at the Taylor's expansion of all these points around that, right? So we consider Taylor expansion, and what we have is that the fx star plus, oh no, it all disappeared. X star is a local minimum of the function. This is equivalent to fx is less than fx, okay? For all x. X is in this, okay, in the neighborhood, and x is not equal to the point x star. Okay. Now we consider the Taylor's expansion of f about the point x star, okay, for all x in this neighborhood. So what we do is that the f x plus lambda p. P can be any arbitrary vector, right? As long as the lambda is very small, right? This lambda is very small, is equal to f x star plus the gradient transpose lambda p. Okay, let me lambda p transpose mathematics of x star plus alpha lambda p, right? And times p, where alpha is between 0 and 1, and the lambda p. Here we have to assume, because the point x star plus lambda p is in this neighborhood, so that means the norm of lambda p must be less than the radius of this neighborhood, right? Right? Am I right? The distance this distance is, well, you can say epsilon. Epsilon must be less than epsilon v, right? So, and that is the alpha, the norm of alpha p must be less than alpha v. To make the x star plus lambda p lays inside the neighborhood. Okay. Now let's look at this. Now we will use the continuity property again. From the, you see that p transpose, you see that when if the gradient, no, I have to be very careful, otherwise I will erase everything again. This is this one go to 0, right? But if the gradient vector at the point x star is 0, then this term, the second term on the right hand side, goes to 0, right? Now we will look at the okay. Now we will look at this. The other term, so the third term on the right hand side, this. Now you see that because the heterometrics is positive, is PDF, right? Positive definite matrix. Then that means P transpose B grad F x star is positive, right? And when this is positive, okay, well, I think here we can just say x should be x transpose grad fx, x transpose the heterometrics of the function f at the point x star times x must be a positive number, right? And because this is continuous, therefore the property, the positive definiteness cannot change immediately in the vicinity or in the neighborhood of the point x star, and then by the continuity of the Hessian matrix, we have the Hessian matrix of the function f at the point x star plus alpha lambda p, okay, must be positive. Yeah, and this multiplied with the okay, this is a positive semi-definite, right? then you multiply with the P transpose P, it gives a positive number. Okay. Now you see that this one, so we conclude that the second term is positive. It's strictly positive. When we say strictly positive, that means it cannot be zero. Okay. So now you see that fx star. Now we go back to this equation. Okay. This one. Now you see that this, okay, this on the right hand side, one term is zero, right? The second term is zero, and the third term is a positive number. Then fx plus a positive number must be greater than fx, right? And therefore, we conclude that fx star plus lambda p is greater than fx star, and hence x star, and this happens for any direction p, for any vector p, right? So we conclude that so fx star plus lambda p is greater than fx star for any vector p such that lambda, the norm of lambda p is less than epsilon bar. Sorry? I'm sorry. Yes. This is fx star is less than fx star plus lambda p. And this happened to, okay, for all for any vector p such that the norm of the lambda p is less than epsilon bar, which is the radius of this neighborhood, the open ball. Okay, and hence the point x star, hence x star is a local minimizer of f and QED. Now, do you have any question? I think the proof of this one, the proof of the second order sufficient condition is quite straightforward. If you understand the Taylor's expansion, it's very straightforward, right? It's much easier to understand than the first one, which is which we use the contradiction technique. Now we go back to the slide. So you may wonder why we have to do, what is the point of doing this chapter? So from this chapter, okay, you will see that now we have first order. From the first order, I think if we use analytical method to compute a local minimum of a function f, then what we have to do is that we have to set the gradient expression to be 0, right? And then we solve the nonlinear equation. We find all the x that satisfy the grad fx equals 0, right? and for all x, it may have many solutions, but one of the solution, if a local minimizer exists, then one of the solution of the equation grad fx equal to 0 is must be a local minimizer of the function f, right? So in using numerical method to compute a local minimum of the function f, we use the same, but we solve the nonlinear equations by numerical method. That's a primitive idea. But in numerical method, we enforce the condition that the cost function or the objective function is reduced in every iteration. When we solve it, you see if you have a maximum or a minimum, then when you solve that by analytical method, you don't know that. And you have to test it, right? Whether it's fx is greater than other points or fx is less than other, right? Then, but in numerical approach, we solve the set of first order necessary conditions, which is the gradient of f is a zero vector. This is a set of nonlinear equation, right? Am I right? This is a set of nonlinear equations. So in the grad f star equals 0. This is a set of nonlinear equation. Right? This is a set of nonlinear algebraic equations. Right? So we find solving this set of nonlinear equations, we have what we call a stationary point. Solving this, there is a technical term, it's a stationary point. A point x star is said, or is called a stationary point. Is called a stationary point of f if the gradient of the function f at that point is a zero vector. Okay. Once we define this, then it's easier to explain. You see that, right? When solving the equation gradient of fx star equals 0, we have a set of stationary points, right? Then if the function f has a minimum, then one of the stationary point is a local minimizer. But how can we find that? I think by hand or by using analytical method, we solve that and then we test each point, right? In numerical approach, we use iterative method to compute a stationary point, okay, plus something which ensures that the function f is reduced in every iteration to increase the chance that the algorithm will converge to a local minimizer. Okay, in this way, at least the algorithm, if we can ensure that the cost function is reduced in every iteration, then it's unlikely that the algorithm will converge to a maximum point, right? No, it cannot be. It can converges either to a local minimizer or what we call a saddle point. Once we have a solution, then what we do is that you have to test it. If this point is really a minimum point, and what we do is that we use second order sufficient condition or second order necessary condition. If the H matrix at that point is not positive semi-definite, then we can conclude straight away that that is not a local minimizer, right? And if we use the second order sufficient condition, then if the gradient is 0 and the H matrix at that point is positive definite, then of course we can conclude that that is really a local minimizer of the function f. If we don't have any information about the function f, then this is the best we can do. When the function f, when we don't know if when we don't know whether the function f is convex or non-convex function. Okay, that means assume that f is a non-convex function. Then this is the best we can do, or we can find a local minimizer of a function f, but that's not a problem. Okay, in many engineering applications, right? But then if the function f is a convex function, then any local minimizer gives the global minimum. That's the property of a convex function. You have to prove this in the second homework. Okay. And then you say that and the H matrix of the function f plays a very important role, because in the homework you will see that, okay, you will prove this result. If the H matrix of the function f is positive definite at the, okay, if the H matrix of the function f at the point x star is positive definite, then in the neighborhood of the function f is a convex function. F is a convex function in around its neighborhood. And if we find that, sorry, that's the, okay, but in general, if the H matrix is positive definite for all x, then the function f is a convex function. This is how we know. Okay, we don't to consider to test whether a function is convex or non-convex. You see that using definition is very difficult. Using the definition is not easy to use, right? It's difficult. So the result that you will prove in the homework is very useful. As long as you can prove that the H matrix of the objective function is positive definite, then the function f is a convex function, and therefore any local minimizer gives the global minimum, right? But here we don't go through the proof. That's I leave it as to you to do the homework. There's too much details to cover. Otherwise, we'll spend too much time. Okay. Then I think, okay, I will, if there is no question about the homework, I'm sorry, if there is no question about the lecture, okay, I'll stop recording and we'll have some discussion about the